All right, friends, welcome back. Today we're going to finish chapter 19, and though I didn't really intend to, we'll move actually on to chapter 20. We're going to need a little bit extra time there to get started, and even if you're not ready to move on to chapter 20, if you haven't done anything in it yet, what we talk about will be pretty good introduction to it. So last time we were talking about how to identify molecules that were aromatic versus not aromatic, versus anti-aromatic, and we had discussed the molecular orbitals of the aromatic rings as the basis for the 4n plus 2 rule or the 4n rule for anti-aromatic molecules. Along the way, it's somewhat helpful to have in your mind just a general picture of the relative energy levels of orbitals in aromatic types of systems. And there's a mnemonic device that works sort of miraculously well. And it gives you the answer that we got last time for sort of the benzene ring orbitals, where you have one orbital that's lower in energy, and then you have pairs of degenerate orbitals. And so it's not worth a whole lot of time talking about this mnemonic device, but it's useful enough that I thought we'd say it. What you do is you draw a circle, and then you look at the ring, and this works for simple aromatic rings that are regular sort of polygons, like a hexagon, and then we'll draw a hexagon. And so see if it's gonna, nope, if I do it all at once, it'll make a lovely, still not, okay, come on, it was supposed to, there we go. Look at that, isn't that lovely? So that's not perfect if you look at it like, oh, okay, all the internal angles are not 120 and all the lines are not perfect. If you could draw a perfect hexagon, what we do now is actually gonna be quantitative. It's really kind of crazy that it works out. You take that hexagon and you move it into the circle. That's why they call it the inscribed polygon method. You inscribe the polygon on the circle. And then every place where that polygon touches the circle is the location in energy of a pi molecular orbital in a 6-membered ring that's aromatic. So one of them here, and you put the polygon one point down, okay? 2 of them here, 2 of them here, and then 1 of them there. And you can draw a line across the middle diameter of the circle, sort of halfway up the circle. And this is the dividing line between bonding orbitals and anti-bonding orbitals. And it turns out the energy differences between the orbitals are pretty well to scale in this system to what they actually are in the benzene molecule. It's kind of crazy that the geometry works out that way. But what this allows you to do then is to tell, okay, this ring that has 6 electrons in the pi system is aromatic because I fill the lowest energy orbital and then I fill the next degenerate pair. I fill them completely, I have no unpaired electrons, and I'm not filling any antibonding orbitals. And that's how you can tell that something's aromatic. That picture you don't necessarily need to decide whether something's aromatic or not, but as long as you know the 4n plus 2 rule, but it can be somewhat helpful, especially in visualizing why anti-aromaticity is so bad. We'll do that in just a second. For this 5-membered ring, as an example, you would draw a circle with a pentagon in it, point down. You don't even need to do that if you don't need it to be quantitative. You can just remember that the orbital picture is going to look something like that. Can you see in your mind where I would have got that from if I'd drawn a circle and then put a pentagon in it, 1 point down, then the 2 points here, then the 2 points here? That tells me that in a 5-membered ring with 6 electrons in the pi system, I again populate the bonding orbital, the lower energy one, and then the next degenerate pair, and I leave the anti-bonding orbitals empty. I have no unpaired electrons. Yeah?
Why is it that the other will impair on nitrogen and on the other nitrogen doesn't count?
Yeah, so when dealing with heteroatoms, this is tricky. How do you know whether something counts or not? And the answer is it depends. And I know you love the answers that just depends. Well, here's what it depends on. Only lone pairs that are in p orbitals count. Lone pairs that are in sp2 orbitals perpendicular to the pi system don't count. So for example, for this nitrogen, the nitrogen is sp2 hybridized. It's surrounded by 3 groups. This carbon nitrogen and this carbon nitrogen bond both come from sp2 orbitals on nitrogen. This carbon nitrogen pi bond must come from a p orbital on the nitrogen. Therefore, the only other place for that lone pair to be is in an sp2 orbital. That would mean it's perpendicular to the system of pi orbitals. It's not participating, and so it doesn't count. Over here, looking at that nitrogen, some of you would have looked at that and said, oh, that nitrogen's sp3. And you could be forgiven for that because that's sort of what you were taught to think about molecular geometry. Is that nitrogen surrounded by 4 groups? Yes. But you're wrong. And the reason you're wrong is that lone pair is adjacent to a pi bond. When a lone pair is adjacent to a pi bond, it will be in a p orbital so that it can participate in resonance or conjugation with the adjacent pi bond. Yeah?
Going back to the 5 number range that you decided, why is there 6 electrons?
There are 6 electrons here because we're only counting the electrons that are in pink. The reason we don't count this lone pair is because it's in an sp2 orbital and it's not in the pi system. The reason we do count this one is because that lone pair is in a p orbital. You can tell that it's in a p orbital because the nitrogen is not currently using a p orbital for a pi bond, and the lone pair is adjacent to 2 other pi bonds. So because it can be in a p orbital, it will be in order to participate in resonance and conjugation. Is that, yeah? Other questions? Yeah.
So if it's an oxygen atom that's adjacent to a pi bond, and it has 2 pairs of
Yep.
pairs, would it count would both pairs count as p electrons, or?
Yeah, so let's do an example of that. Here's a molecule that I'll just tell you is aromatic. Clearly the pi bonds count. How about the lone pair on this nitrogen? Does that count? Nope, because it's in an sp2 orbital. Now what are you going to do with that oxygen? Well, again, you could be forgiven for saying that the oxygen was sp3 hybridized. But one of the lone pair, the oxygen is adjacent to 2 pi bonds. That means one of the lone pairs is going to be in a p orbital so that it can participate in resonance and conjugation. The other lone pair cannot be in a p orbital if the other one already is. It must be in an sp2 orbital. So on an oxygen, only one of the 2 lone pairs can be in a p orbital. So looking at that, we would only count 6 pi electrons, and we would conclude that that molecule is aromatic. All right? So to decide about lone pairs, look at the heteroatom. Is it already involved in a pi bond? If so, the lone pair can't be in a p orbital. If it's not, look and see, is there an adjacent pi bond? And if there is, then the lone pair will be in a p orbital so that it can participate in resonance. Yeah?
For it to be aromatic, does it need to be adjacent to 2 pi bonds, or can it be adjacent?
I think in most of these rings, it's going to be adjacent to more than one just because it's a fully conjugated ring. But the idea that if a lone pair is adjacent to a pi bond, it's going to be in a p orbital to be stabilized by resonance is true, even in not aromatic molecules. Yeah?
So they took out the bottom pi bond, would it then be aromatic? Then you just have like a hydrogen.
So, right, so you're asking, what about this molecule? What if we just did this? That is no longer fully conjugated. Do you see how the carbon with the two hydrogens is an sp3 carbon and there's no p orbital on it? As soon as the molecule is not fully conjugated, it is just not aromatic, and the number of electrons don't matter anymore. Yep. Yeah.
Is there ever going to be a situation where the oxygen and the nitrogen are both adjacent to the pi bond, and like you have to consider which lone pair would win in that situation?
No. So I think actually this. I'm trying to think of a situation that describes what you've described. Let me just do this one. It's not exactly what you've described, but it's similar enough. And the answer is no, there's no competition. If these are both adjacent to pi bonds, the lone pairs are both going to be in p orbitals. Yep. I want to come back to this one in just a second, but let's quickly do this 8-membered ring. Just do the inscribed polygon method. You need, this is a 1, 2, 3, 4, 5, 6, 7, 8. So we need one that's lower in energy, 2 pairs, so that's 1, 2, 3, 4, 5, 6, 7, 8. Now the way the geometry works out, it turns out that those middle 2 orbitals, that degenerate pair is actually, if we did this via the inscribed polygon method, you would see that those pair of 2 orbitals in the middle lie right along the starting point, the sort of the interface between bonding and anti-bonding orbitals. This is roughly the energy of non-bonding lone pairs. If we fill up these orbitals with the available electrons, 2, 4, 6, 8, what we see for this anti-aromatic molecule is it looks like it has 4 pi bonds, but what you see is I only have 3 pairs of electrons in bonding orbitals. The remaining 2 are in non-bonding orbitals and unpaired, and so it's a diradical. It's not even a lone pair, it's a diradical. So that tells you that this structure for this molecule is looks deceptively stable unless you know the 4n rule for anti-aromaticity, because the actual structure of this molecule is it's basically a diradical. Yeah?
So if it's basically a diradical, do we still draw it with the appearance of 4 pi bonds, or how would
We do draw it with the appearance of 4 pi bonds, but you got to know that it's super reactive.
Okay.
Yep. Now, and that's true for this. Let's talk about this molecule that I just drew. Based on our discussion, you would count the following electrons. It's cyclic, it's fully conjugated. One of the lone pairs on each oxygen can be in a p orbital. The other must be in an sp2 orbital, right? Therefore, how many electrons that are involved in the pi system do we have? 8, right? So we would say that that's anti-aromatic. Now let's just do that inscribed polygon method again, only I'm going to copy what we've done earlier because it's going to apply. It's the same shape as the benzene ring, only now I have 8 pi electrons. Where's the only place I can put those extra electrons? Up in those antibonding orbitals. So now this is not only a diradical, but those electrons are higher in energy than they would have been had they just been lone pairs. Okay? So that tells you how destabilizing anti-aromaticity is. Now, I told you last time to put an asterisk in your head, in your mind, about anti-aromaticity, because you can tell that that's so unstable that if the molecule has other options for rearranging its shape that might lower these electrons in energy, it'll take them. So let me show you what happens to this molecule. But before doing so, I want to point out, if you see this structure, you should call it anti-aromatic. So what the molecule will sometimes do is anti-aromatic molecules frequently distort their shape. distort their shape, often out of planarity, with the goal of breaking conjugation, because to be conjugated, all the p orbitals have to line up parallel to each other. So if they can distort their shape to break that, then they will escape anti-aromaticity, and they will just be not aromatic. So an example of that with this molecule with the two oxygens is the two oxygens will bend up out of the plane of the ring to make this, I'm trying to draw it, but I'm failing at it, this sort of pseudo boat-like structure. I'll just try again. There we go. The two oxygens will pucker up, or maybe one will pucker up and the other will pucker down out of planarity. That breaks conjugation. In this example, the oxygens go from being sp2 hybridized to something more like sp3 hybridized. And what does that do to the orbitals? When you break conjugation, that makes it, and you break aromaticity, that means you no longer have degenerate pairs. One moves down, one moves up, and now the two electrons that used to be equal in energy in a diradical now just drop down to a regular energy level. So by breaking conjugation, by distorting from planarity, anti-aromatic molecules can escape their horrible fate, and so they often do. The challenge with that is sometimes your text, knowing that, in fact, I think this is a problem from your text. Your text will look at this and say, oh, that's just not aromatic. And what they're doing is they're going through the process all the way to completion saying, okay, well, it would be anti-aromatic, but it's going to distort its geometry so that it can avoid anti-aromaticity, therefore we're just going to call it not aromatic. That's a sensible conclusion, but it's confusing, and it skips the step of realizing that if it were planar and if it did have a planar geometry, it would be anti-aromatic. So what I want you to do when you see something like this is you need to conclude that it is anti-aromatic, all right? For us, the term not aromatic is simply going to be reserved for things that are not fully conjugated. For example, this molecule here is not aromatic. Why? Because it's not fully conjugated. Or this molecule here is not aromatic. Why? Because it's not even cyclic. But we will call this molecule anti-aromatic. All right? Yes?
So are there any cyclic anti-aromatic rings that can't pucker that have to maintain their shape, and that's hard?
It's a good question. Are there any cyclic molecules that can't pucker? I think the smaller ones have a more difficult time. Cyclobutadiene, though, even that will stretch out a little bit to make the sigma bonds a little bit longer, and it will twist the pi bonds a little bit out of planarity. So even the smallest rings will try to do this. Even so, if you were to look at cyclobutadiene and call it, well, just not aromatic, you're missing something really important.
But it's not diradical at this point once it puckers, once it stretches.
Once it stretches, yeah, what happens when you stretch is for the cyclobutadiene, if it were in its perfectly symmetrical and planar form, it's the diradical. If it stretches, one of those drops down a little bit lower in energy, and now you're to something like that. It's still really reactive. In fact, you can't observe cyclobutadiene unless you're really low temperature. We're talking 4 Kelvin, almost to absolute zero. So it's pretty dang reactive. Saw another hand. Anybody? No? Okay. All right. So continue to practice that. You can ask questions about aromaticity that are more complicated than just, is it aromatic or not? For example, looking at this, I could ask you, what kind of orbital holds this lone pair? What kind of orbital holds that lone pair? You'd answer sp2 and p respectively. And understanding that reflects being able to demonstrate that reflects your understanding of aromaticity. Another way to ask the question is to say, here are a couple of hydrocarbons, a 5-membered ring and a 7-membered ring. Which is more acidic? Now, when you see that question, which is more acidic, suddenly you're scrambling. You're looking back at the pKa table. Was I supposed to memorize something? Did we learn anything in 351? pKas. What you're not realizing is this is actually a question about aromaticity. And the way you get there is by calming down and remembering how we deal with acidity. And that is, we often rationalize acidity by thinking, what is the stability of the conjugate base? So go ahead and draw the conjugate base of both of those molecules. And then let's draw the conjugate base of this molecule. And realize that asking which hydrocarbon is most acidic is exactly the same as asking which conjugate base is most stable. Now, can you see how to connect the stability of these conjugate bases to aromaticity? What do you notice about these two? Are they cyclic, fully conjugated? How many pi electrons does the one on the left have? 6, right? How about the one on the right? Therefore, the one on the right is what? Anti-aromatic. Remember that anti-aromatic means that it is especially unstable. So, the aromatic conjugate base is most stable. Therefore, this starting material had to be most acidic. You don't even need to know a pKa to tell that. You just reason it through by thinking about what the conjugate base is. Okay, you can ask actually this same sort of question in a slightly different way, which I've done before and is kind of fun. For example, take the same 5-membered ring, but now instead of 2 hydrogens, let's put a leaving group, a chloro. And then let's do the same with the 7-membered ring. And I've been told my 7-membered rings look like sad robots. And once I saw it, I can't unsee it. So there it is. So I could ask which reacts faster in an SN1 reaction. And if you're not careful, you think, oh, SN1, that's in 351. Why is he asking us about that? And the answer is because I'm evil, but it is also because it has to do with aromaticity. So remember that SN1 reactions involve a leaving group leaving. And remember that the speed of the SN1, because that first step where the leaving group leaves is so uphill, the speed of that first step is related to how unstable or stable the resulting carbocation is. So take a first step, get started by showing the leaving group leave. And then let's draw the resulting carbocationic intermediates. Then we're going to ask a question about which of the carbocation intermediates is more stable. I tried to make him happy. Okay, so count the electrons. Which of these is aromatic? Which of these is anti-aromatic? Yep, this guy is anti-aromatic. That's why he looks angry. And this one is aromatic. So you would predict that this one would react fastest in an SN1 reaction. Okay? So be able to use the concepts of aromaticity to answer questions about molecules. There's a lot of good questions in the end of chapter about this. Go ahead.
Is that 7-membered ring fully conjugated?
Yes, is that 7-membered ring fully conjugated? Yes, so is the 5-membered ring. The reason is this positively charged carbon is sp2 hybridized, and there's from our perspective an empty p orbital on that carbon that can line up with all the other p orbitals in the molecule. Okay, yes?
So in that case, it's only fully conjugated once a proton's been removed and it becomes an ion.
That's right. So both of these questions involve starting materials that are just not aromatic, but intermediates that either are or are anti-aromatic. Yep. Good, yes?
So is that a 7-member ring or how many rings?
Yeah, that's 7. Yep. They're hard to draw. If you want to know how to draw a 7-membered ring, I always draw one of them flat. Then I splay out the sides a little bit more than for a 6-membered ring. Then you need 2 there, and then you need 2 there. And it ends up looking kind of wonky, but it's the best we can do. Incidentally, the prison on Narkina 5 in Andor was in the shape of a 7-membered ring. I thought that was awesome. If you don't know what I'm talking about, you should watch Andor. It's one of the better streaming Star Wars series. Although my wife tells me I'm so undiscerning about Star Wars. She's like, I don't even have to ask you, Josh, did you like it? Because the answer is yes. Did you like the Book of Boba Fett? Yes, loved it. Did you like Obi-Wan? Yeah, it was great. What'd you think of Ahsoka? Loved it. So anyway, how about the sequel trilogy, the controversial sequel trilogy? Well, I liked it. Yeah, I still liked it. If it's Star Wars, then that's for me. All right, well, as I said, I wasn't totally planning today to move on to Chapter 20, but I think you'll want a little bit more time in Chapter 20. So we're going to get started on that now. And everything we've done so far is set up for understanding the different reactivity of benzene rings versus other alkenes. So, for example, in 351, you learned that alkenes, in the presence of electrophiles, do addition reactions. We're not going to go through this mechanism, right? But basically, when an alkene attacks an electrophile, you lose the carbon-carbon pi bond, and you lose a bond in the electrophile, and you get 2 new sigma bonds. And the product is what we'll call an addition product. The problem with that for benzene, if you were to pretend for a moment that one of the pi bonds in benzene was just like an alkene, the proposed addition product for benzene has a key problem, and that is what? Go ahead. It doesn't become anti-aromatic, but you're right, it loses aromaticity. It becomes flat out not aromatic. The reason you can tell that it's not aromatic is because it's no longer fully conjugated. So an addition reaction for benzene, we would lose aromaticity, and accordingly, that doesn't happen. In fact, if you put benzene in with just bromine, nothing happens. You get no reaction. Now, it turns out you can coax benzene into reacting as a nucleophile. But you will see that the products we get from that are not addition products. And how we deal with aromaticity is a key consideration. The other thing that you're going to see is that in order to get benzene to react as a nucleophile, we need a more reactive electrophile than we've typically dealt with so far. Remember that what makes bromine a good electrophile is 2 things. First, the Br-Br bond is weak, and second, the leaving group, Br- is very stable. But that's not good enough for benzene. We need an even better leaving group. So how do you make bromine more reactive? And the answer is we're going to use a Lewis acid to make one of the bromines an even better leaving group. The Lewis acid we're going to use is iron tribromide. Now, you don't need to know about the bonding in iron tribromide at this stage, or really ever in this class, other than to say that iron tribromide has an empty orbital that's low energy and that can accept electrons from bromine. So watch what happens when you add iron tribromide to Br2. The empty orbital on iron's low enough in energy that lone pairs on the bromine attack it, and you end up with this molecule where the bromine is now in the middle is now bonded to two things and has a positive formal charge on it. Now, if you thought Br minus was a good leaving group, this one is even better. This one will leave as FeBr4 minus. The negative charge that would have been on the bromine is now delocalized over a much larger molecule. So what we've done by adding the Lewis acid is we've turned this molecule into a super electrophile, and that's because this is a super leaving group. So now that electrophile is reactive enough to react with benzene, even though benzene's aromatic and super stable. So we've souped up the electrophile, and then let's draw what happens. The first step is going to be very similar to what we saw for alkene addition reactions. You're going to take pi electrons from benzene, and we're going to start with one of the 3 pi bonds in benzene. Even though we understand that actually benzene's electronic structure looks like this, you have 2 electrons in a degenerate pair of orbitals, and one of those 2 is going to react. We're not going to worry about which one reacts. It's fine for drawing the mechanism to start with one of the pairs of electrons, understanding that the one that reacts is going to be one of the 2 that are higher in energy. Then we'll break the bromine-bromine bond and the leaving group leaves, and we get an intermediate. And it's an intermediate that's similar to intermediates we saw for alkene addition reactions. One of the carbons of this pi bond is going to get the bromine, and the other is going to get a positive charge. Now, because our starting material is benzene, we're not worrying at this point about whether carbon 1 or 2 gets the bromine, because carbons 1 and 2 are identical. There will come a time soon, Friday, when carbons 1 and 2 won't be identical anymore, and we'll have to make a decision about which carbon gets the bromine or the electrophile. That's called regioselectivity, and there's some pretty straightforward rules for navigating through that. For now, we won't worry about it. That first step of this reaction is an addition step, because we've added bromine to the molecule. But look at what we've done. I feel like we should tell this intermediate to go to its room and think about what it did, because it's no longer fully conjugated. You've got an atom that's sp3 hybridized in the ring, so we've lost aromaticity. It's no longer aromatic, meaning that this first step is pretty uphill in energy. What will happen next is different from what happened in the alkene reaction. In addition to alkene's reaction, a nucleophile would have come in and attacked this positive charge. Instead, what happens is an elimination step. And what we do here is going to look like an E1 reaction. On the carbon that has the bromine, you also have a hydrogen, and on the adjacent carbon is a positive charge. So what will happen is a base, usually Br2, but I'm just going to be generic about it. Sorry, usually Br minus as a base, would come in and remove this proton. It doesn't need to be a very strong base at all, because the conjugate base of this acid, this proton, is super acidic. The conjugate base of the acid, you will see, is aromatic and very stable. When we do that elimination step, we lose the proton, but we restore aromaticity. So that's a drop down in energy quite a bit. Aromaticity restored. And overall, this reaction, these two steps of addition and elimination, are called a substitution reaction. We call it electrophilic, meaning you need a good electrophile. Aromatic, meaning your starting material is aromatic. Substitution, we call it substitution because we're replacing, in the starting material, we're replacing the hydrogen with the bromine from our electrophile. And that pattern of make an electrophile, have benzene react, lose aromaticity to get a carbocationic intermediate, then deprotonate that intermediate to restore aromaticity. That pattern unifies all the reactions that we'll talk about, all the new reactions we'll talk about in this chapter. Okay? Questions about that? Yeah?
So that first step, addition, is probably, the rate determining the slowest part.
Yeah, you would expect exactly that first step to be rate determining because you're going from something that's aromatic to something that's a carbocation. So this energy diagram, if we drew it, should look really similar to an SN1 reaction. Yeah?
So breaking the aromaticity and then restoring the aromaticity is a common step between all.
That's right. Yeah, you will see that as a pattern in all of the reactions that we introduce. I saw another hand. Yeah?
Would adding the bromine make the benzene ring any more or less stable?
Would adding the bromine make the benzene ring any more or less stable? Good question. And yes, the answer is that sometimes the groups that we put on the benzene ring are going to increase or decrease the reactivity of the benzene ring. There are two major effects that we'll talk about. One is basically electronegativity, and the other is resonance. And I'm going to punt on that for a minute until I have a better example to talk about. Yep. What else? Okay. You can do this with not only, of course, bromine, and the conditions, if you want to see this in a sort of predict product sense, it's just Br2 and FeBr3. You can also do it with chlorine. And in general, at least with these iron Lewis acids, they tend to match the substituents on the iron with the halide that you're using. I don't actually know what would happen if you tried to use FeCl3 up here and FeBr3 down here. This reaction overall is called aryl halogenation because you are putting a halide on a benzene or aromatic ring. Aryl is the abbreviation we use for aromatic hydrocarbons in the same way that alkyl is the abbreviation we use for just regular hydrocarbons. Yeah?
Is there any fear that this reaction will happen multiple times,
Yeah.
conferring multiple bromines onto the aryl ring?
Yeah, is there any chance that you could do multiple halogenation, put multiple halides on the ring? Yes, if the benzene ring is reactive enough. And this gets to the issue that you just asked about, is the benzene ring more or less reactive after we add a single bromine? And the answer is that halides have two main features. Let's just start with the chlorine. Halides have electronegativity. And so you would expect the halide to withdraw electron density from the ring just through a bond dipole kind of thing. I'm going to call that EWG, where EWG stands for electron withdrawing group. So by virtue of its electronegativity, you expect the chloro to withdraw electron density from the benzene ring. That would tend to make it less nucleophilic. But there's another effect, and that is that the halide can be an electron donating group via resonance. I will show you how this is done. You can tell it's an electron donating group by resonance because you've got a lone pair adjacent to the pi bonds of the benzene ring. When that's true, the atom can donate its electron density to form a new pi bond with the first atom of the benzene ring. And then to accommodate that, you have to move electrons from a pi bond of the benzene ring onto one of the atoms of the benzene ring. This is one of the resonance structures that you can form from a halide donating electron density into the ring. I'm not going to draw you all three resonance structures, but, and I encourage you to do that sometime today or tomorrow, convince yourself that this lone pair can be on these other two pink atoms. So two different effects from a single substituent. And halides are kind of weird. We're going to see that there are, when we consider whether a group is a donating group or a withdrawing group, there's two major outcomes that we want to deal with. One is, how does it impact the nucleophilicity of the benzene? And second, how does it impact the regioselectivity of another reaction that you might do? We're not ready to talk about regioselectivity, and we'll have more to say about the nucleophilicity of the benzene. For right now, I would tell you that experimentally we observed that chloro and bromobenzenes are a little less reactive than benzenes are. So it must be in the case here that for the reactivity of the benzene ring, the electron withdrawing group dominates. We'll have more to say about that later. Okay, yeah?
Is that resonance structure still aromatic?
Yeah, so is the resonance structure still aromatic? Hard to tell, and it's probably a minor contributor because you don't want to mess with aromaticity. But the presence of those negative charges or the potential for the chloro to donate electron density into the ring is important later on. So, yeah. So that's okay, you've been exposed to it. We'll talk about it a little bit more later, but yeah, the idea of does the group we just added to the benzene influence subsequent reactions, that's important. All right. So it's okay if you're worried about that. We got a little bit more complicated than I intended to at this stage, but it's okay to see that more complexity is coming a little bit later. I want to introduce the next reaction, which is called aryl nitration. And in this reaction, you take a benzene ring, you use nitric acid and sulfuric acid, and it installs a nitro group on the benzene ring. And it's probably good for you to start drawing out the Lewis structure of the nitro group because its structure is going to help you understand some important things about the nitro group. The electrophile in this reaction is NO2+. And you get that from nitric acid and sulfuric acid. And if you want to see how that happens, it's not particularly difficult, but I'm not going to hold you responsible for it. And so if you want to talk about it some other time, you can come see me in my office or come up after class and I'll draw it for you real quickly. For now, it's enough to know that the presence of sulfuric acid and nitric acid makes this NO2 electrophile. So what happens next is pi bond of benzene attacks the electrophile at the positively charged nitrogen, and we have to break a nitrogen-oxygen pi bond in much the same way that we did in carbonyl chemistry. We make a new carbon-nitrogen bond, and then the other carbon from that pi bond has a positive charge on it. Then in a second step, a base, probably the conjugate base of sulfuric acid, does the elimination step, and we restore aromaticity to get that product. So following the same pattern of addition to a high energy electrophile, then elimination to restore aromaticity. Why would you want to put a nitro group on a benzene ring in the first place? Sometimes that nitro group can change the properties of the benzene ring in interesting ways. The other reason you'd want to put a nitro group on a benzene ring is that you can do a reduction reaction afterwards using a reagent that you've seen before. This is hydrogen and palladium on carbon. and that can convert the nitro group into an amino group. And there's a non-standard name for benzene rings with nitrogens on them that I tend to use out of habit that I'm just going to tell you now. It's not important to memorize. It's just important to understand when I talk about them. Benzene rings with amino groups on them are called anilines. So this hydrogen and palladium on carbon reduce the nitrobenzene to the aniline. And in so doing, that's a pretty dramatic change. And you can see that if you start to consider the various properties of the nitro group versus the aniline. So let's take a look at that nitro group. I want you to notice that the atom that's bonded to the benzene ring, the nitrogen, is positively charged. I also want you to notice that that nitrogen is doubly bonded. It's involved in a pi bond with oxygen, an electronegative atom. When you have an atom adjacent to the benzene ring that is pi bonded to an electronegative atom, that is a classic situation in which you can draw a resonance structure that withdraws electron density from the benzene ring. So here is one of those resonance structures. As before, I'm just going to draw one of them for you, and then you can draw the remaining ones. And I want you to be really clear about which atoms in the benzene ring share the positive charge. Sorry, we got a little bit cramped there. So you can see that by resonance, I can move electron density out of the ring to form a new pi bond, and that leaves the positive charge here. And you should be able to see how I can similarly put that positive charge on those other pink atoms. So the effect of the nitro group, we would call the nitro group an electron withdrawing group by resonance. You also expect nitrogen to be more electronegative than carbon, so it's probably a withdrawing group by electronegativity as well. This is going to have impacts on how nucleophilic the benzene ring is and on the regioselectivity of subsequent reactions. But notice how that changes when we get to the aniline by the reduction reaction. Notice that in the aniline, the nitrogen has a lone pair on it. And anytime the atom attached to the benzene ring has a lone pair on it, that is a situation in which you can donate electron density into the ring to generate this resonance structure. And again, I'll just draw you one, and then you can draw the others. In this resonance structure, what used to be the lone pair is now in the pi bond, and there is now a negative charge on the adjacent carbon. And by resonance, you should be able to see that that negative charge can be in the benzene on those two other atoms in the ring. So we're going to call the aniline nitrogen an electron donating group via resonance. You would say that the nitrogen's more electronegative than carbon, and so you'd expect it to be somewhat withdrawing by electronegativity. So you'll see sometimes there are groups where electronegativity and resonance give you the same answer. Sometimes there are groups where electronegativity and resonance give you different answers. And we're going to have to learn which effect dominates in a context-dependent way. All right. Well, I think we've still got a couple minutes, maybe 1 minute, but I think I'm done and I'm thirsty. So we'll call it a day. See you Friday.